Okay, welcome back everybody to a new window of Wolfram Mathematica, which is a tool that I use for all of my mathematical quandaries. In the last video, I ended by copying the model we derived from we fit our data to in Excel, and I'm going to paste that into Mathematica here, tidy that up a bit. That's supposed to be an exponent. So again, this is y, or the period of our pendulum, is equal to this constant times x, which is, or I should say this, y is our dependent variable, the period of the pendulum, x is our independent variable, the length of the pendulum, and the model is that y is equal to x raised to this power, then multiplied by that constant. And we are asked to compare this model to the actual equation for a pendulum's period, which is as follows. Let me set up a text cell here. Try that again. There we go. Window, not magnification. I want toolbar. Format. Oh, it's already there. I had it from earlier. What? Bear with me. Okay, here we go. So, the period of the pendulum, t, equals 2 pi times the square root of its length divided by the gravitational acceleration, g. So, what we are asked to compare is this formula we found with Excel to this formula. Now, the first thing to note is that Excel defaults to using x as an independent variable and y as a dependent variable, whereas the convention you'll find in textbooks is that the independent variable of our pendulum is L, while its dependent variable is T, again for length and period. So the first thing we're going to do is make that change used to Excel notation. Okay, and then the next thing we are doing is I'm going to take this square root of g that's in the denominator of this fraction, and I'm going to move it underneath the 2 pi. So we have, that's not what I wanted, square root of g. Get rid of that from here. And then finally, we have the square root of x. Now hopefully you remember from middle school or whenever people first learn about powers of things, that the square root of something is the same as taking that something and raising it to the 1/2 power. And of course, 1/2 can be written as 0.5. So now this should start looking familiar. We have x raised to the 0.5 power versus x raised to the 0.431/9 power. Let's look at this coefficient, 2 pi over the square root of g. This is, in fact, something we can calculate since we know what 2 pi is. That's 2 times 3.1415 whatever, and g in the units we have been using, which is centimeters for length and seconds for time, is 980 centimeters per second as opposed to 9.8 meters per second. If we calculate that, oh my god. And I just got a complaint from Mathematica. I don't know if you saw that, so I'm going to try something else. Copy as plain text. Get rid of this. Paste. Okay, so now it's interpreting that as it is. 980 centimeters per second. Evaluate. And we get that, of course. So let's evaluate with floating point decimal precision. And we get that. Okay, so turns out that this fraction here, 2 pi divided by the square root of g, is equal to 0.022, or whatever, 0.200709. Compare that to our Excel model, which is 0.285. And we're going to take this number, put it into here. Aha! So we took this equation for the period of a pendulum, which you can look up in your textbook, and we converted it into something. We rewrote it into a form that looks suspiciously familiar to our Excel equation up here. Let's clear this junk out of the way since we don't need it anymore. In fact, I can make it look even more similar by taking this and doing that. Let's clear. Let's see. I'm just going to move this down here. I don't know if you can hear those squirrels fighting in the background, but it's a very terrible noise, and naturally they're fighting throughout this entire recording. Or you can hear those squeaking brakes in the background. Anyway, so what did we do? We took this theoretical model, we rewrote it in that form. In fact, I'm just going to get rid of this because we don't need it anymore. So this is our theoretical expression for the relationship between a pendulum's length and its period, and this is what we got in Excel. And they are very similar to each other. 0.285 is almost 0.200709, and 0.4319 is almost 0.5. Groups from my other section were, when we figured out how to do all this stuff, groups from the other section actually managed to collect data that was produced a fit that was even closer than the sample data from the Lab 2 PowerPoint, which was quite impressive. But now that we have these models, we can answer the questions from Part L and M. Part L asked, what is the period of a pendulum whose length is half of a meter, or 50 centimeters? We can answer that using both of these models. So I'm going to take this one here, just going to copy that stuff to the right side of the equal sign, paste it in here, using a little Mathematica magic. Actually, what I'll do is I'll just go ahead and replace this x with 50, since we're using units of centimeters, and that's what we get. We get a period of 1.54394 seconds. If we take our model, or the theoretical model, and we do the same thing, that's not what I wanted. Copy as plain text. Okay, we're going to replace x with 50 once again and evaluate. We get a period of 1.41923 seconds. So these results are pretty close to each other. Neat. And then the other question was, what is the length of a pendulum whose period is 5 seconds? So that's just taking these equations and inverting them, solving for x, and replacing y with 5 for 5 seconds. Mathematica can do that very easily, and I'll start by doing it with the theoretical model. Forgot to copy as plain text, so I'm just going to copy that. Say this is equal to 5. Replace 50 with x, and tell Mathematica to solve. And it complains about using an inverse function, but I don't care. It gives us the result that that pendulum is 620.6 centimeters long. So that's a little more than 6.2 meters. somebody at the end of class came up to me with the result that they had calculated of around 600 meters, and I couldn't figure out where the error was in their math. I suspected it was a unit conversion error, but then what I discovered with a group in the following section was that if you type in to a calculator 5 divided by 2 pi, it very easily interprets that as 5 divided by 2 times pi. So in other words, you type in 5 divided by, you type in what you think is this, which should evaluate to that number, but your calculator interprets it as this. Come on. Well, you can see here it's moved the pi up into the numerator, which evaluates to a number that's about 10 times greater. So that's where that power of 10 came from. Stupid calculators. Anyway, that's just a little side point. The real point for everybody to see is that we're able to calculate a length from the theoretical model, and then we can do the same thing from our Excel model. 5 equals that. Solve. According to our data-derived model, the pendulum is going to have to be about 760 centimeters long, so a little more than 7.5 meters long, which is much smaller than when we figured it was like 13,000 feet with that factor of 10 error. Anyway, so this is how you do the analysis in Excel, how you fit your data to in Excel to produce a power function that is similar to, there we go, to produce a power function that is similar to our theoretical model. I hope this helps. I hope this was somewhat illuminating. If you have any questions, feel free to email me, and I will explain to the best of my abilities. We can also meet in person, perhaps, because I assume you're going to have to know this stuff for your lab reports. So, yeah, definitely, if you're confused about any of this, don't hesitate to set up a meeting with me, because it's easier to explain it all to somebody beforehand and have them get it right on their lab report than it is to go through and comb through the lab report and figure out where the mistakes are and all that good stuff. Plus, it makes you guys have a better grade, and that's part of my goal as your TA. So, thank you for watching, and see you next week.